All right, so we are going to look at example 7.5 when we have structures that do not obey the octet rule. All right, let me fix it there. Okay, so the first example is XeF2. So Xe is xenon. Okay, it has 8 valence electrons. Each fluorine atom has 7 valence electrons. So that's 14 plus 8. So that's going to be 22 electrons. All right. So here we're going to put xenon, and then fluorine is going to be the terminal atoms. I'm going to go ahead and draw a structural arrangement here so that we have single bonds in between the elements. So fluorine has 7, 2, 3, 4, 5, 6, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And then xenon has 8. 1, 2, 3, 4, 5, 6, 7, 8. So we should have 22 electrons total. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay. And then xenon itself has 2, 4, 6, 8, 10 electrons around it. So it has what's called an expanded octet. Okay, so obviously more than 8. Of course, each fluorine atom has 8 electrons. Next example, xenon F6. All right, so xenon again is in the center. We have 6 fluorine atoms. I'm going to draw out here. Okay. And then I'm going to draw out my little structural formula here where we have single bonds in between the elements. Now I'm going to assign the 7 electrons for each fluorine. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so each fluorine has 8. Xenon has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it has 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14. 14 electrons around it, so of course it's expanded. And so that should be the structure for XeF6. All right, going back to our textbook here, we need to go ahead and move on to the next section, which is related to Lewis structures, and that is calculating the formal charge. So most of you have done this. If you've already done the lab from last week, if you stayed over, you had some problems where you're having to calculate formal charge. Formal charge is useful when we're trying to determine if we have 2 different structures and we're trying to determine which one's more likely. Calculating formal charge is going to be a way to figure that out. So how do you find the formal charge on an element? The number of valence shell electrons to free atoms, you take that number and subtract it from the number of lone pairs minus half of the number of bonding electrons. Okay, so here, example 7.6, calculate the formal charge from the Lewis structures. Assign formal charges to each atom in the interhalogen ion ICl4-. All right, so here's the structure, and we're going to assign formal charges on each atom. Okay, so here I drew out the structure here, and this is overall has a negative charge there. So when you want to put a bracket there and indicate the negative charge, just like you would an ion, you have to indicate that it's not neutral. Okay, so for each chlorine atom, what we're going to do is, if we go back to our formula, let me push this up here. So the formal charge is equal to the number of valence shell electrons. Okay, so for chlorine, so formal charge Fc is equal to, and this is going to be for chlorine, is equal to the number of valence shell electrons. So for chlorine, it should be 7, right? For a neutral atom of chlorine. And so 7 minus number of lone pair electrons. Okay, so there are 1, 2, 3, 4, 5, 6 lone pair, so minus 6. So that's lone pair electrons. Okay. And then minus half of the number of bonding electrons. Okay, so here I have 2 bonding electrons, right? So here I have 2 electrons. Half of 2 is 1 electron, right? So minus half the number of bonding electrons, so minus 1. Okay, so 7 minus 6 is 1. 1 minus 1 is 0. So the formal charge on this chlorine atom is 0. All right, so let's look at the next chlorine atom. Okay, so a neutral chlorine atom should have, again, 7 valence electrons, minus the lone pairs, so 1, 2, 3, 4, 5, 6, minus half the bonding electrons. Again, we have 2 bonding electrons, so half of 2 is 1. So we get a 0 again. So the other 2 chlorine atoms, same story. 7 minus the lone pair, 6, minus half the bonding electrons. There's 2 here, so half of 2 is 1 again. And you get 0. So we have 0 formal charges, and what you'll see here when they assign formal charges, a little number in parentheses. That's telling you there's 0 formal charge here on the chlorine atoms. Okay, so what about for iodine? So what is the formal charge for iodine? So number of valence electrons for a neutral iodine atom, you look that up on the periodic table, it's 7. That's a halogen. All right, so minus the lone pairs, 1, 2, 3, 4. So 7 minus 4. And then half of the bonding electrons. So here we have 2, 4, 6, 8. Half of 8 is 4, so minus 4. Okay, so you see 7 minus 4, that's a negative 1. Okay, so we have a negative 1 formal charge on the iodine. Negative 1. That means it has an extra electron. And that makes sense because you see our overall charge on the structure is a negative 1. And you see that here, and it should be represented here when you have a formal charge of negative 1 overall, the structure should be negative. If you have a negative 1 and a positive 1, the structure should be neutral. Okay, in this case, we have an extra electron that happens to be on the iodine atom, and so it has a formal charge of negative 1. Okay, so here's another structure where we're trying to assign formal charges to each atom in the molecule. So here for chlorine, the formal charge is going to be the number of electrons for the neutral atom, which should be 7, minus the number of lone pair, which is 2, 4, 6, minus half the bonding electron. So here we have 2, half of 2 is 1. And so we get a formal charge of 0 for chlorine. Okay, we look at this one, same scenario, 7 minus 6 minus 1, that's 0. 7 minus 6 minus 1, 0. Here for bromine, so formal charge for chlorine is 0. Formal charge for bromine is going to be, so neutral atom is 7 valence electrons, minus 1, 2, 3, 4 lone pair, minus half of the 3 bonds here, so 2, 4, 6, half of 6 is 3. Okay, So 7 minus 4 minus 3, that's 0 as well. And so each atom in this structure has a formal charge of 0. And so obviously it's a neutral atom or compound because you don't have any positive or negative charges that cancel out or anything. Everything's 0. And so you have 0 formal charges on each atom in that compound. Okay, so now we're going to look at formal charges to predict molecular structure. And so here there's some criteria in order to do that. Of course, the highest preference would be given to structures that have no formal charge on every atom in the structure. Also, if you have some formal charges, the arrangement with the smallest non-zero formal charge is preferable. So if you do have some non-zero formal charges, the smallest values would be more preferable. If you have adjacent formal charges that are 0 or of opposite sign, they also have preference. And then if you have to choose among several Lewis structures with similar distributions of formal charges, the structure with the negative formal charge on the more electronegative atoms is preferable. Okay. All right, so here we see an example with carbon dioxide. So here we know that the less electronegative atom should be in the center. So the formal charges here are going to show us why that's the case. So here we have two structures where carbon is the central atom, and then we have a structure here where oxygen is the central atom. And so notice they've already assigned formal charges for each atom in the compound. And you can see here we have 0 formal charges with this structure here, the first one. The second one, we have a positive 1 on oxygen and a negative 1 on oxygen. And here we have a positive 2 formal charge on oxygen and a negative 2 charge on carbon. So you can see why oxygen isn't going to be a central atom and why we have the rule that the least electronegative element should be in the center. And that's because oxygen is never going to have a formal charge of positive 2. Okay, I mean hardly ever. I'm not going to say never, but oxygen is more electronegative than carbon, a lot more. So it wouldn't have a positive formal charge for sure. And here we have oxygen having a negative formal charge and a positive formal charge. That's no good either. So obviously the structure that has 0 formal charges on each atom would be the more preferable Lewis structure. All right, but what if we're comparing 3 different compounds? They each have 3 different elements. Okay, so here we see different elements in the center position there. And note that carbon is the least electronegative of the of all 3. Okay, and so if you look at the formal charges here, you have a negative 1 on nitrogen, 0 on sulfur, negative 2 on carbon, 0 on sulfur, positive 1 on nitrogen, negative 2 on carbon, positive 2 on sulfur, and negative 1 on nitrogen. So obviously with our rules here, several reasons why we would choose the first structure. The first structure has the least number of formal charges. It only has a negative 1 value on one atom. The others are zeros. Also, it places the least electronegative atom in the center. Okay. And so the first structure would be the structure that has the least number of formal charges and would be the most likely structure to be correct. All right, so here's another example. We have 2 different structures. All right, so you're going to be given problems like this where you have 2 different structures. You have to assign the formal charge. So let's go through this here. So nitrogen has, normally as a neutral atom, it has 5 valence electrons, right? So 5 minus number of lone pair, 4, minus half of the bonding electrons, so half of 4 is 2, okay? So 5 minus 4 minus 2, that's going to be a negative 1. Next, nitrogen here, again, has positive 5 is number of valence electrons it has. So 5 minus half of the bonding electrons, which is 2, 4, 6, 8. Half of 8 is 4. So 5 minus 4 is positive 1. For oxygen, you have 6 valence electrons. 6 minus 4, which is 2, minus half of the bonding electrons, which is 4. Half of 4 is 2. So 6 minus 4 minus 2 is 0. All right, next atom here. So same thing. We have the same situation here. So it's negative 1. Here we have oxygen, which is 6 minus half the bonding electrons, 2, 4, 6, 8. Half of 8 is 4. So 6 minus 4 is 2. We have a positive 2 there. Nitrogen is 5, has 5 valence electrons. 5 minus 4 minus 2, 4. Half of 4 is 2. So 5 minus 4 minus 2 is minus 1. All right, so here are the formal charges for each element in the compound. And so now we're having to figure out which structure is the best. Okay, so first of all, we notice that nitrogen is in the center here and oxygen is in the center there. Again, we know that the least electronegative element is going to be nitrogen and not oxygen, so this would be more favorable. Also, we have, in value, we have a positive and a negative. Okay, we said when they're adjacent to one another and opposite in signs, that's more favorable too. So we would have to choose this first structure here as it being the more probable because it has least number of formal charges and it has least the least electronegative element in the center. All right, so our last topic in this section here is what's called resonance. So resonance is something you're going to see a lot in organic chemistry. So I don't know if you've noticed or not, but sometimes when you draw out a Lewis structure, you can see that there are 2 possibilities for the double bond. You may have thought maybe, there's a reason why it should be on the right and the left. And the case is that it can be on either the right side or the left side. So here we have a 2 different structures. They basically have oxygen on both sides, and so you have nitrogen in the middle. So you have a double bond between nitrogen and oxygen, but do you put it on the right side or you put it on the left side? Well, it actually can be on either side, and so you represent that by what's called resonance structures. Okay, it's basically writing out all the possible structures that it could possibly be. So when you have, a molecule that's symmetrical, and you can basically figure out that there are 2 different possibilities to write the structure, and either one is correct. Okay, these are referred to as resonance structures. All right, so we generally write a double-sided arrow to represent resonance structures. Okay, so here you see that you have a central carbon atom, and then you have 3 different oxygen atoms, and this double bond can be in 3 different places, right? And so with a resonance structure, you're pretty much just showing all the possibilities of where the double bond can be on the left side, on the right side, or at the top. Okay. And so that's general with resonance structures. So when you're drawing out Lewis structures and you have two possibilities, it's common to actually show all possibilities. So I'm not going to specify that particularly. Normally, what I'll have is I'll have a resonance problem where I'll tell you that this compound has or I'll ask maybe how many resonance structure a compound has, and you can draw the Lewis structures out and then figure out how many it has based off of the Lewis structures. Okay, so be prepared to know how to do that for the test. All right, we have 2 more sections left in Chapter 7. The next section is all about the bond strength of covalent bonds. Okay, so when it comes to bond strength and covalent bonds, and we kind of saw some of this in our handout on Wednesday, when we're talking about energy of bonds. So here, if we have X and Y, we have maybe we have a single bond between X and Y. When that reaction occurs, we have decomposition reaction. You're going to be able to determine change in the enthalpy is going to be basically the amount of energy that it took to break that single bond. Okay, so here, for example, we have H2. So H2 gas, hydrogen gas, has a single bond between each hydrogen atom. Okay, so the amount of energy it takes to break that bond is 436 kilojoules per mole. Okay, that's the standard enthalpy for the reaction, and so that's how much it takes in order to break that single hydrogen-hydrogen bond. So here we have another example where we have a molecule with 3 or more atoms, and they have 2 or more bonds. The sum of all the bond energies in such a molecule is equal to the standard enthalpy change for the endothermic reaction that breaks all the bonds in the molecule. So for example, the sum of 4 CH bonds energies in methane is 1,660 kilojoules, is equal to the standard enthalpy change for the reaction. Okay. So the average carbon-hydrogen bond energy then would be 1,660 divided by 4, which is 415 kilojoules per mole, because there are 4 moles of carbon-hydrogen bonds broken per mole of the reaction. Although the 4 carbon-hydrogen bonds are equivalent in the original molecule, they do not each require the same energy to break. Once the first bond is broken, the remaining bonds are easier to break. Okay, so the 450 kilojoule per mole value is the average. It's not the exact value required to break any one bond. Okay, and there's some reasoning behind that, why the first one's harder to break than the second one, and so on. So what about bond strength, comparing bond strength and distance of the bond? So the strength of a bond between 2 atoms increases as the number of electron pairs in the bond increases. Okay, so generally, as the bond strength increases, the bond length decreases. So the shorter the bond length, the stronger the bond. So we find that triple bonds are stronger than double bonds. Okay, and then double bonds are stronger than single bonds. So single bonds are longer in length than double bonds. Double bonds are longer in length than triple bonds. So here we see sort of a summary of those trends. Here we see bond energy, and if we compare the bond energy of a nitrogen-nitrogen single bond compared to that of a nitrogen-nitrogen double bond, or even a triple bond, you see that the bond energy increases as the number of covalent bonds increases. Now, if you're going to compare those same values here, actually we don't have those values, but if we were to compare them with bond length, if we compare carbon-carbon single bond, carbon-carbon double, and a carbon-carbon triple bond. You see here that the length of the triple bond is a lot shorter than that of the double or the single. So the shorter the bond, the shorter the bond length, the stronger the bond energy will be. And you see that here, same trend. And so on your worksheet on Wednesday, you had to look at bond length and bond energy. And you saw that relationship between bond length and bond energy. So we can use bond energies to calculate the approximate enthalpy changes for reactions where enthalpy of formation values are not available. Okay, this calculations will also tell us whether the reaction is exothermic or endothermic. We know an exothermic reaction has a negative delta H, heat is produced. It results when bonds in the products are stronger than the bonds in the reactants. Okay, so I told you guys earlier a scenario where for every chemical reaction you have bonds that are being broken and bonds that are being formed. So an exothermic reaction happens when the bonds that are being formed, more energy is released during that process than it takes energy to break the initial bonds. With endothermic, the opposite is true. It takes more energy to break those initial bonds of the reactants than it does energy that's released after the formation of the new bonds. Okay. So enthalpy change for a chemical reaction is equal to the sum of the energy required to break all the bonds in the reactants. Okay, so we see this formula here. Enthalpy is equal to the sum of all the bonds broken minus all the summation of all the bonds formed. Okay, so when we do this calculation, we're going to have a chemical formula, okay, and then or a chemical equation, and then we're going to have to break it down in terms of if the reactants and products have single bonds or double bonds or what. So you have to figure that out using your Lewis structures. Okay, you're going to have to draw out a Lewis structure to figure out does does hydrogen have a single bond, a double bond, a triple bond? Because some diatomic molecules have singles, but I mean sometimes you end up having like carbon monoxide, for example, isn't going to have a single bond between carbon and oxygen. So you have to really write out your Lewis structures in order to figure out the types of bonds that these molecules have between one another. Okay, and then you're going to have to look up these values. So here we have an example of hydrogen and chlorine reacting to form hydrochloric acid. It's a balanced equation here. And so here, for one H2 molecule, you have a single hydrogen, single bond between the two hydrogen atoms. For chlorine here, again, you have a single bond. For hydrochloric acid, you have a single bond between hydrogen and chlorine. But you have, it has to be, the reaction has to be balanced. So, of course, you have two of these, right? So you have two HCl bonds here. So here they're calculating the enthalpy here for the reaction. And so they're adding up the values for a single hydrogen-hydrogen bond. So that energy, if you look it up, for a single hydrogen-hydrogen bond energy there is 436 kilojoules per mole. So 436 kilojoules per mole. And then plus, so bonds broken. So they broke, bonds broken, of course, are for the reactants. Cl-Cl single bond. Let's see where we can find a Cl. Cl single bond. It should be somewhere. There we go. So it's 243 kilojoules per mole. So 243. So bonds broken, so those are the reactants, minus bonds formed. So 2 times, because I have 2 moles, right? So we need to find a single HCl bond. So if we look up here, a single HCl bond is going to be here. So it's 432 kilojoules per mole. So 432 times 2, right? And then when you do the math, you get a negative 185 kilojoules. So the negative value tells us the enthalpy is negative. It's an exothermic reaction. Okay, so that's telling us it takes more energy is released when the bonds are formed than when the bonds are broken. And you can see that here, right? I mean, this is giving me over 800. And then here we only have like 600 and change. So you can see that in the math part of it.